Good evening. My name is Shreyas Jaikumar, and my fellow teammates are Akshaya Rajakumar and Siddarth Sadeesh Kumar. We are part of Team 3, and this is the demo video pertaining to Lab 6 Quad Hardware Threaded ARM ISA Compatible Processor Core Net FPGA. So the first part of this labs is deliverable is that we have to decide on the ISA, and we decided to go with the official ARM ISA. In particular pertaining to the 70 DMI processor, wherein we followed the exact 32-bit split up. That is, the first 4 bits is for the conditions, the various conditions, the 16 conditions involved, followed by the type of the instructions used, the opcodes, etc., the NZCV flags, which updates accordingly when the set bit is set, or for certain instructions like compare, CMN, and etc. Irrespective of the set bit not being set, the flags are going to get updated. For like the I-type instructions and the load word and the stored word instructions, such as like the PUBW L bits, wherein P indicates for the pre and post indexing. If L is 1, it indicates the load word instruction or a store word instruction, and etc. Just not going to go into the full details of it, but long story short, yeah, we went with the exact ARM ISA, and we decided to proceed that way. So as you can see in this manual, so basically like they have given a C bubble sort program, and we have to like decide with as I specified earlier in the video, like what the what instruction set that we should use, and as specified, we went with the official ARM ISA, and we were able to implement almost a good amount of functions, like almost all the widely used R-type, I-type instructions, LDR, STR, which is basically load data to the register, store data from the register to the memory, load word, store word instructions, all the control flow statements, like all the conditional branch statements, like basic branch if equal to branch greater or BGE, BLT, and also unconditional branch, jump and link, and etc. Branch and link in this particular ISA. So for that, obviously, going by the manual and decoding each type of instructions, looking at the opcode bit split, and then manually noting or jotting that down, and then coming up with the logic pertaining to our control unit was kind of a Herculean task, which is why as specified in this lab manual, we first came up with a Python script, wherein if we provided the inputs, like the hex inputs, that would correctly decode what those hex digits translate to. Like it would generate the 32-bit instructions. It would generate the 32-bit instructions it would generate the 32 bits pertaining to that respective instruction with the split up, and also what the instruction is. So yeah, I'm just going to show that script. So that is the script. It's as you can see here, it's reverse engineering .py implemented in Python. So yeah, I'm not going to explain line by line of the code. But as you can see, yeah, we have defined these how we need our opcodes to be broken down for data processing, like the bits 24 to 21. So the first part, okay, it goes from 31 through 0, right? So the first 4 bits is the condition code. So basically, the commonly used condition is 1110, which stands for always. And based on certain other conditions, for example, like for equal to, for not equal to, for greater or equal to, for less than, greater than, and etc., it's going to be like different conditions. So basically, it's like a total of 16 conditions. I'm going to touch upon that when I get to the pipeline data part.v, because there it's like a proper nested case statement there, which shows all the different conditions and how the respective operations happen. So then comes the opcode bits again, again 4 bits for the opcode, which indicates what operations has to be performed, arithmetic operations such as and, sub, logical operations such as or, XOR, and etc. And yeah, so as you can see here, then basically we need to extract, we have defined a couple of parser line functions and certain helper functions in order to extract the respective mnemonics by giving in the commands. So that's why, as you can see here, what is a mnemonic, right? It depends on the opcode condition and whether if it is an immediate or a register operand. And yes, there's also a set bit here. Technically, because if the set bit is set, meaning if it's 1, then the flags N, negative, Z for 0, C for carry, and V for overflow will be updated accordingly based on the respective operation. But for certain instructions, like in particular 4 instructions, those 4 instructions are these: TST, TEQ, CMP, and CMN. For them, the set bit does not need to be set. They are going to update the flags either way. So yeah, so then I have given a detailed if-else statement for the different type of instructions type by splitting the opcode, by splitting the entire 32 bits as to like how we want. So for R type, it's going to be the first 4 bits, it's going to be the condition bit, and then it's going to be the type of the instruction, then comes the opcode, then the set bit, and then the source, destination, and the 12-bit operands. Then for load words, it's the same. 4 condition bits, 3 bits the type of instructions with PU, BWL, which I just touched upon. P stands for pre or post indexing. I believe B stands for if it's going to be byte addressed and etc. L for sure, I know that it stands for if L is 1, then it's a load word instruction, else it's a store word instruction. And then comes the source, destination, and the 12-bit offset. So based on all the different types of instructions encountered, branch is very important. So branch has a total of 6 bits with 26 bits, 24 bits with 2 bits, 26 bits offset. Yeah. So I'm just thinking. So just going to give a quick run through of head to toe scan of the code. So as you can see, this is the entire bubble sort in hex, and we want it to be categorized in these in these respective categorizations: R type with immediate, LDR, STR, LDM, STM, branch, so that it's like it will be like much easier for us to reverse engineer the logic and implement it in our Verilog files. So yeah, so I'm just going to run this real quick. Yes, so as you can see here, it's like I'm just going to give a rerun it. Yeah, so as you can see, so all the R-type instructions are being categorized with the respective bit split for the instructions: R-type with immediate, LDR, STR instructions, LDM, STM, and branch. Okay. Now moving on to the actual logic / the implementation part. Okay, so obviously in the last lab we didn't need to use ALU in our closed pipeline, but here obviously we need to set we need an ALU. So yeah, so basically like what the key part of this, I'm just going to go really slowly and then explain what is important. Yeah, so basically based on the type of instructions, be it an R type or an I type, etc. R type is the most, like, let's tackle R type first. For R type, so it's 4 bits are set for the opcode, which leads to a total of 16 conditions. So as you can see here, if it's 4 zeros, it's AND, if it's 3 zeros and 1, it's XOR. And from here on, right, like for example, this 0010 stands for sub. So based on that, I'm not going to again explain line by line of the code, but so for all these instructions, we need the set bit, right? So if the set bit is set, then the flags accordingly carry, overflow. Here only carry and overflow are used, but the 4 flags that are used, that are present is NZCV, as I said earlier, negative 0, carry out, and overflow. They will be updated accordingly based on the type of operations. And yeah, so after having referred the ARMS 70 DMI manual, like what flags should update, what should not update, what combination should update, and etc., we implemented this logic over. We implemented the flags update logic based on that. So yeah. So the second part of the code is for LDR STR instructions. So this is yeah. So basically, yes. Now I remember. So in PUBWL, as I said, P bit is used to determine stands for pre or post indexing, like whether if it should be pre or post indexing. The U bit is used to determine whether the offset address is added to the base address or subtracted from the base address. And depending on the meaning, if it's like 1, it's going to be added. If it's 0, it's going to be subtracted. This, as I said earlier, B bit stands for byte or word, and L bit indicates whether if it's a LDR, that is a load word, or an STR, store word instruction. So basically what we do here is the calculation of the offset address, and yeah, that's it. This is just nothing. It's just basically for branch instructions. So basically, if the type is going to be 0, 1, then it's you're not going to use the ALU for branch instructions, right? So yeah, it's just a generic line of code over there. So then comes the control unit. So okay, based on the type of instructions used, that is for R type instructions, for I type instructions, LDR STR instructions, and for branch instruction, and also for unconditional branch and link. This indicates that, for example, like, so when it's an R type instruction, so basically again the key part is we are writing the value to a destination register, ergo read write is 1. For load word and store word instructions, like you know, for store word instructions, we are going to write to the memory, therefore memwrite is going to be 1. But for load word instructions, we are going to read from the memory. We want the contents of the memory and not the ALU. We are going to read from the memory and also write it to the register, and therefore reg write and mem to reg is 1 accordingly. This indicates branch instruction, as you can see, 101. So basically here branch control signal is just going to be 1, and yeah, all the others are 0. And for debugging purposes, we have commented this out, but for branch and link, reg write is also going to be 1 because we are going to write to the link register, in particular register number 14. So we are going to save the return address, we're going to write the return address to that particular register. So this is like a quick summary of the control unit.v. And then comes, okay, I'm not, to be honest, I'm not going in proper order, but yeah, this is this is the Verilog file pertaining to the program counter, and basically there's nothing to explain over here much. It's, you know, if it's reset, PC is going to be set to 0, else PC is going to be incremented by 4, that's it. This we already talked about, the register file contents, the Verilog file pertaining to the register file, and yeah, so 16 registers, each 64-bit wide, that's it. So we're just initializing that over there. Okay, now comes the pipeline data part.v, wherein this is like the entire 5-stage pipeline processors as UDP implemented in Verilog file. Again, I'm not you know, like give a proper line-by-line explanation of the code. It's going to take a real long time, but just going to go as quickly as possible. So we are going with the module instantiation of the pipeline underscore data path. Then we are calling in the program counter by you know, calling in all the respective functions from program underscore counter. And then, oh yeah, just like the last lab, both the IMEM instruction memory and the data memory, we used IP cores generator, that is in particular the you know, project new sources IP core generator. And then for the instruction memory, we chose a single port ROM, and for the data memory, it was a dual port RAM. For the instruction memory, because of the fact that each instruction is 32-bit wide, the width is 32 bits, and the depth is 256 8-bit address. For the data memory, the width is 64 bits and the depth is 512. And accordingly, for testing purposes, we downloaded the appropriate COE/coefficient files into IMEM and DMEM from a simulation point of view. We will get to that later in the video. So yeah, so that's what this is. This is the IMEM instantiation in the pipeline skeleton. Then comes, yeah, I'm just going to quickly go through this. Yeah, so this is stage 1 to stage 2. So we have a total of 6 stages, because in the manual it was specified that we could change the UDP as per our needs. So we went with 6 stages. So then comes the control unit stage 2. So this is what I already talked about earlier. The condition bits are going to be mapped from 31 through 28 from the entire 32 bits in accordance with ARM's official ISA. The split up happens, right? So yeah, so that's what happens over here. Control unit instantiation. Yes, this is what I talked about earlier in the video. So basically, again, for the 16 conditions, right? So basically, for the 16 conditions, there is a total of 16 conditions. As I've commented over here, equal, not equal, greater than, less than, etc., etc., etc. So based on those 16 conditions, the flags accordingly are going to be updated, right? Yeah. So this is the same logic even for conditional branches. So for example, if the branch is taken and if this condition is met, then it's going to be BEQ. If the branch is taken, if it is a branch and if this condition is met, then it's going to be BNE. By the same logic, all the 16 conditional branch statements were also implemented and tested. So yeah, just gonna quickly go through it. Yeah. So as you can see, initially we went with, instead of testing out signed numbers, we tested with unsigned numbers, and therefore we have zero extended it for branch and load word LDR/STR instructions accordingly. So 6 bits plus 24 bits plus 2 bits, 32 bits in total, 20 plus 12 bits accordingly. So as you can see, the extension happens. So this is what I talked about earlier. If it's a branch and if its condition met, then the branch is going to be taken. And then comes the register file instantiation. Then it's just pipeline stages accordingly. So as you can see, stage 1 to 2, stage 2 to 3, 3 to 4, 4 to 5, and etc. So this is just like kind of a repetition of what happens earlier. So it's all the control signals are just going to propagate through the pipe. Okay, this is an important stage. In the previous lab, this stage was a dummy stage because there wasn't any ALU used, but here is where the ALU from ALU.v is being instantiated, being used in pipeline_datapath.v, and accordingly, yeah, so for leg 1, it's going to be RS, the first source, and for leg 2, depending on whether if it is an R type or an I type, it's going to change, right? So yeah. We need the zero extended offset for I-type instructions, but for classic R-type instructions, we just need the second source's data. This is the capturing of the flags. Like once the set bit is set and what the flag and whatever the flags are updated post the ALU execution that's going to be captured in flag out. We latch that. We latch the flag output. Right, yeah. So yeah, just gonna quickly go through this, pretty much boilerplate. Again, just like what I talked about earlier, this is the DMEM instantiation. Nothing much to explain over here. Just yeah, so basically we're done. That's it. Yeah. And then comes the final write back stage, wherein like if the signal is true, either we need the data from DMEM or the ALU data. And yeah, basically, so this from a skeleton, the pipeline underscore datapath.v skeleton is done. And yeah, I believe I'm done. So now my fellow teammates are going to, move all these files into Xilinx ISC 10.1, along with, as I said, I'm sorry, IMM and DMEM. By instantiating the instruction memory and the data memory, we are going to show a live simulation for a bunch of instructions, just to show that all the instructions that are being supported by us. So yeah, thank you.
So this was the code which is given for the bubble sort, and we have to convert this into the assembly code, which we have done here using ARM commands. And we also ran another command to take the disassembly. So if we run the command, we were able to get the hex codes, like as we can see here, we can get the hex codes here. So what we did was essentially we took these hex codes which were given by the ARM compiler, and then we had to decode the codes so that we could find the fields, like the correct fields for each instruction. So we had done that, and we have decoded for all the instructions in the bubble sort. We had used this as the reference. And we had mapped the bits to the functions, and we had decoded the assembly.
We stuck mostly to ARM ISA in order for future compatibility with other functionalities we want to implement. We just didn't want to change the ISA like a little bit or like any part of it. Just go with the ISA so that in future we want to upscale it to other like functionalities for our GPU or the final project. It's better for us to stick with ARM ISA in that sense. So we didn't do much change to the actual ISA codes.
So, coming on to the simulation part, we had taken all the, like, we had built the pipeline, and we attempted to execute each of the instructions that we had decoded from the compiler, like the compiler given hex codes. So for this, so we are decoding the instruction here, like this is the instruction stage 2, and then we are decoding it like according to the ARM ISA, and then we are passing it. So we also have a control unit here. So what it does is essentially like the control unit takes in the instruction, and then it decodes it out to like specific one hot coded signals, so that we were able to control the memory registers, everything. So we had categorized R type, load store, and branch. So these are the control signals for that. And then also in the pipeline data path, this is the whole pipeline data path. And then
these are in ARM ISA we have something called as conditions, for which we check for the flags in case of like any branch operations. We want to check, and there's some four flags called as NZCV, negative, zero, carry, and overflow. So you have to check those flags, and based upon that, if those flags match with the current condition-based flags match with the current flags, then you will take like a branch operation for that. So for that we have this whole system for logic for that. We built it around that,
Yes.
and then
So this will depend on the ALU flag out. So if the ALU flag out matches with the condition field of the instruction, and if they are equal, like if they match, the instruction will execute, or else it will be converted into a bubble. So here we have the sign extension offset, and coming down, yeah, we have
this is all
like
pipelines.
pipeline stages.
Yeah.
Yeah.
Moving on to ALU. So this is go.
Yeah.
Okay. So for ALU again, we stuck with the ARM ISA of course and designed our ALU based upon that. We didn't do much of a scale up from the initial ALU we developed, because again we want to stick with the ARM ISA stuff, and yeah, based upon whatever opcode we got from ARM ISA, like what are the for whatever functionality what the opcode is, based upon that we just built our own ALU on that. And yeah, we have an art type. For art type, we are checking a separate unit, and also for art type is going to be based on the opcode. And for load word store word, we have something called as PUBL. Yeah. So for that, also we just defined an ALU logic for that. And if it's an art type, we go with this structure. And if it's a load word store word of instruction, which is more, we use this is again a flag for ALUs, and then we use a structure for that. So we have something called BW, p-redexing, post-indexing, unsigned sign, and then branch. I don't know what.
Word.
Yeah. Oh yeah. It's a
Word. Yeah. Word and
word. And so based upon that, we again have an ILE for that. So using ILE, we can do both R type and also an R type and load store types instructions. So we designed our earlier on that. We also get the flags, as I initially said. We have flags NCZB, which again we are getting output from our ALU.
Okay. I also wanted to add that for these 4 instructions for compare, the flags are updated like no matter what.
There's something called set bit which needs to be triggers for us to like update the flags. For these four instructions, we don't need a set bit, and it's going to be automatically updated no matter what the set bit is. Yeah.
Yeah.
This is the ALU logic.
It's the ALU logic, and coming to the pipeline again. Yeah. So we're writing into
So here we made a modification. So for us, we just used a port B of a DMAP for as like a logic analyzer sort of thing, so that we can see what's there written in DMAP will be and see what is written in DMAP and check the data from there. So here in bubble sort also we are writing it to the DMAP, and from DMAP we are able to see what is the output by keeping address B as an input and out from the of the port B out data out as our output, so that we can, when we put an input for address B of the DMAP, we can see what data is written in the DMAP.
Yeah, so basically we are using port B as a read-only port in order to read from the data memory. Yeah, and this is the logic. And I'd like to show the IMEM. So here it's read-only, and then we have a coefficient file with all the instructions uploaded into the coefficients file. So these are the instructions that we have given. So this is in accordance with the ARM ISA.
Due to the lack of FMBs, forwarding multiplication also stalls, we just had loads of no-op for that.
Yeah.
Mitigate that circumstances. Yeah, it was just like a test code for that. So
yeah, to mitigate the dependency issues, we had to insert no-ops in between so that there's no issue while execution. So here we have the simulation results.
Yeah, we can check all our instructions for bubble sort of working. We set multiple UUT so that we can check each and every parameter.
So here we had added the signals, like the internal signals as well, so that we can monitor the register files and also the data memory. So this is the register file. Like, as we can see, according to the instructions, they are being written into the register file. So this is in order of the execution. So now I'll show the synthesis part. So here we have, I'd like to show the IDS.v right now.
So yeah, so for IDs dot we just modify again, like almost like what we did for our last lab, we just modified our IDs dot v pertaining to this. We had a few extra outputs, and yeah, based upon that, we just scaled up from our last lab with IDs dot v.
And yeah, we have
Show all the files we actually have in our SLC also now.
yeah.
Okay. Yeah, so we've had two extra. As we said earlier, we have a software X address beef and hardware X for that, like pertaining to that.
So this address B corresponds to the data memory where for port B, where the data can be read.
Yeah, these are the files we have explored for our synthesis, and based upon this, we are able to get a bitstream.
Yeah, I'll show you the synthesis.
Yeah, these are the bit files.
Yeah, so as you can see, we have generated the bitstream here. XML also. So we have updated the XML file according to the generic software and hardware registers that we had in our IDS.b. And also after synthesis, this is the file where the registers, generic software registers and hardware registers are assigned. So as we can see here, we have addresses for each of the registers that we had defined. So after this part, we had loaded this onto the NetFPGA. So now we'll load it onto the FPGA. Okay, so we have written a Perl code where the registers can be like displayed onto the terminal. So that is, I'll run that. So as we can see here, we have the PC register and the memout low. So since it's like 64 bits, we've just taken the 32 bits, like the lower part. So now
This is basically we're writing to the
Address of the
address B.
B.
Check for the DMEM material or DMEM
Yeah.
content DMEM.
So I'll display the first address.
Yeah, we are getting to 200, which is what we actually have in our DMAP. We're getting it. And also we can see the PC incrementing rapidly, which is what should happen with our case of like every clock cycle. I mean, we're not around 10 nanoseconds, so.
So we'll go ahead and see the second. Yeah, as we can see, we had stored it in this order. So
basically, we're just getting all our sim inputs and outputs, what we need for the sim, and you can actually get all of them just like total. Hopefully, or something. Yeah, so this is what we again from our sim, we think we got this value, so we're just able to see what we actually expected in our sim. We can just find it over in hardware also.
hardware, so yeah.
And yeah, if you want, you can store everything for eBay. And I'll just show the hardware, just the sim part, I guess.
Yeah.
Something like the EE, yeah.
So I'll just show the simulation results as well so that we can compare the results in the hardware with the simulation results.
Okay, so now we are going to just like this is a bunch of assembly instructions. Just show that all the memory instructions, the R-type instructions, some branch instructions, and etc. all work perfectly. So the first instruction is LDR R1, R0, #0. So as you can see, like R1, as you can see, R1 in R1 the data is correctly loaded. And then there's also another load word instruction, LDR R2, R0, 4, data is being loaded. Then the third is also a load data to a register instruction. As you can see, data is being loaded. And the fourth instruction is also an LDR instruction and the data is being loaded. The fifth is an R-type instruction, wherein we are adding R1 and R2's value into R5. And based on that, it's correctly tallying for R5 in the subsequent clock cycle, and the data is being loaded. And then comes a sub instruction, R6, R1, R2, and R6, yes, the data is also being loaded. So in this similar manner, we have, there is a couple of one or two more R-type instructions in the same logic, and then comes move R8, R4, wherein R4's contents is being exactly moved to R8's register, and that has also been clearly verified by the cursor, as you can see in the video. And then comes add R10, R5, R7, which is again an R-type instruction. That has also been correctly verified over there, as you can see from the register data. And then let's so this, as you can see from the flow, like there is a couple of more instructions, but now we want to touch upon the branch instruction. So just give us a minute.
Mm. 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 So the after the
that's it.
Yeah. PC.
yeah, you can this one.
PC so that it jumps.
Wait.
And the compare instruction go branch go PC so that I can say that okay, PC is going, branch is being taken, PC is going.
This. Oh yeah, I think it's here.
Yeah. Okay.
Yeah. So you can see here.
Yeah. So you can see that.
Yeah.
Around.
Mundina branch instruction ka.
Sure.
Okay, now
What do you want to say?
No,
That's fine.
Yeah.
Okay. So when the branch instruction is executed, that is EA0000012, the branch is taken because it's an unconditional branch, so it jumps to the target. And as you can see, yes, the PC is like increasing dramatically, meaning that, as I said earlier, the branch is being taken, so the branch works. And post this is a bunch of str instructions. So basically from the register, the data is being loaded onto the memory. So if we keep running it for some time, I don't know if we'll have time here, but if we keep running it for some time, the registers as contents are all going to be like fully, it's going to 0, and we will get data in the memory. So which correctly confirms or affirms that str instructions also work. So yeah, by summarizing this part, I think we have implemented most of the R-type, the I-type memory instructions, LDR, STR, and also like conditional branch statements, because all the 16 conditions are being met earlier. So we just if it's a branch signal and if the condition is being taken, then BGE, BLT, all the other 16 conditional branch statements was also being supported logically. Unconditional branch, and as I stated earlier in my part of the video, we have also given we haven't tested it out, but we have set the 14th register as the link register in order to just get started with branch and link. And yeah, thank you.
Thank you.